Hello guys, welcome back on African Motives, still on electrical trade theory and working on transformers. We have a question that we are going to be focusing with from the question paper of November 2022. So in this part, we are given a single phase transformer. Take note, this is one of the most common our most common transformers, a single phase transformer. So in this case, it's a single phase. All right, transformer is connected to a 2 kilovolts alternating current supply. So in this case, we are given the voltage, which is the input, that is our V1, as 2 kilovolts, that is 2 kilovolts, current alternating current supply, and it draws a no load current of, so you're given the no load current in this case of 2.5 amps at a power factor of 0.2. So we're given the power factor, which is 0.2 in this case. So that is the information that we're given, and we are given to determine the magnetizing component of the load and so forth and so forth. Okay, so take note, from our presentation, we are supposed to have our diagram in this case of our no load, for our no load in this case as follows. Let's just have it here so that we can just understand some of these basics. So remember that we are going to have here where we've got our voltages. I just hope it's going to be clear so that when I'm explaining some of these formulas, you understand where they are taken from. Having our current in this case and the flux in this axis. All right, so this is what we are going to have. So this is going to be our current. All right, that is your no load current in this case. All right, so this is your no load current, and we are given the angle, which is from the power factor. All right, from the power factor, we are going to have this angle here between the vertical and the no load. This is our angle theta from the power factor here, because remember that the power factor is equivalent to the cos of theta. So the cos of theta gives us power factor, which is also equal to the working current over the no load current. So this all gives us what? The power factor. So this is where we have our working current in this case. This one is where we have our working current. This is our no load current. All right, this is where we are going to have the magnetizing component, which is where we are going to have our IM, in this case, our magnetizing component. All right, so this is what is most important: the no load current, the working current, the magnetizing component, yes, and the voltage and so forth. Okay, so the relationship that we have so far is from this power factor, and also to note that this angle that we see as our theta, this one, our theta, is the same as the angle that is in between here. So we can take it here as our theta like this. So if you have to understand from this diagram, it means that this whole part is your IO. This one is your IW. This is your IM. So we can play around with this theta with any ratio. If you have to check here, when we said cos theta is actually taken from adjacent. This is the cos of theta, which is taken from adjacent over hypotenuse, which is the adjacent according to this theta here. This is your adjacent, which is the working current, over the hypotenuse, which is your no load current. Because according to this theta, we are referring to this angle theta. This is our adjacent. This is our hypotenuse. This is our opposite. This angle here, you refer it inside from which concept? From our Z angles in mathematics, alternate angles. These angles, they are equal. All right, these Z angles, they are equal. So that is how you answer these questions. All right, so the first question, it was on finding the magnetizing component of no load. Okay, the magnetizing component, which is IM. So IM can be taken from this part because we have got this no load current. All right, so we need IM in this case. So let me just have it aside as 8 0.11. So we need to calculate IM, but from which part? If we are to take here, we are going to use opposite. This IM is opposite. This is our hypotenuse. So you can use opposite of hypotenuse, which is what? From sine. So this can be taken as IM is equivalent to the no load current times the sine of theta, which is taken from this part that I'm simply saying to say this is our, from this part here, this is our opposite. So which ratio uses opposite and hypotenuse? That is the sine. So the sine of theta is equal to the opposite over the hypotenuse. The opposite is your magnetizing component. The hypotenuse is your no load current. So you can make the magnetizing component the subject by cross multiplying. This one multiplies 1 times IM is going to be IM is equal to IO times sine theta, which is IO sine theta, which is our no load current. So that is what we can have. But if you are to check, we do not have the theta. We have the no load current, which is 2,5. So where can we have theta? Remember what we said about the power factor here. We said the power factor, it consists of theta. From this information, the power factor is equal to cos of which is 0,2. So meaning to say we can take the power factor that we are given in this case. So from our power factor of 0,2, we can calculate theta. So from power factor, which is equal to cos of theta, we can calculate this angle. So that means our theta is actually equivalent to the arc cos of our power factor, which is 0,2. So our theta, make sure that your calculator is in degrees. The arc cos, that is shift cos on your calculator, 0,2 gives you 78,463 in degrees. So this is the theta that we are going to use to calculate our magnetizing component in this case. So from our formula of IM, we said in this case, our IM is going to be IO, which is 2,5. So that's 2,5 times the sine of theta, which is our theta, that's 78,463 degrees. All right. So we can calculate our IM in this case. So 2,5, if we are to multiply times the sine of 78,43, you're going to obtain something like 2,44, 2,44925, and so on. So if we are to round off to 3 decimal place, this is going to be 2,449. This 2 cannot change the 9, which is measured in amps. This is current measured in what? Current measured in amps. All right, so that was our magnetizing component due to the what? Due to the no load current that we are given. Then the other part of the question is to calculate the core loss component of no load, okay? So the core loss is given as IO, that is our IC in this case, all right? The core loss is taken from the cos of theta. So let me just write it this way. All right, so this is 8.12. So we have to calculate IC, which is the core loss. So IC is equal to IO cos of theta, which is simply the power factor in this case. So our IC is simply IO, which is our no load. Our no load, remember, is 2,5. And this is going to be 2,5 times the cos of theta. Remember, we said power factor is equal to cos theta. So this cos theta simply represents the power factor, which is the power factor is 0,2. So we're going to multiply to 0,2. So meaning to say this is no load times power factor. We can simply use our formula like this. Okay, so this is going to give us 0,5 in amps. This is current, which is measured in amps. All right, so these are the typical questions, very, very typical. They'll ask you these typical questions like this. You have to be careful how you apply the formulas, the use of formulas, and also understanding just the basic part of your diagram on this part. All right, so that was our question, having 5 marks. Then we move on to 8.2, where we are given to briefly explain the operation of a single phase transformer at no load. That is the one that we had at no load. But can we describe its operation at no load. That is 5 marks for that. Okay, so let's check what we have in this case. All right, so the transformer at no load, we are given that when the alternating voltage is applied to the primary winding, an alternating current flows through it, which steps up an alternating flux in the ion core, which links the secondary winding, inducing in it an EMF of the same frequency. So that is the idea that we have at no load. Okay, so these are the typical questions that you're supposed to be used to in your answering criteria, because they can ask any part which is related to this on transformers on your final exam. So more questions as we move on as a family of Mason African motives. Let's continue to work with revisions, question papers, and also referring to our textbooks for more, so that we can understand how do they ask these questions and how are we supposed to answer the typical questions. But for now, that's it, guys, for Mason African motives. Till we meet again.